Okay, so now we're doing nuclear. And we'll start with the introduction. We'll talk about radioactivity, types of radiation, and half-lives. This all should be kind of a review from Gen Chem. Will help you with your quiz. So how would you define radioactivity? Release of particles from unstable nuclei. Someone add to that definition. Let's find it a little bit. Is it just particles? And energy, right? Because gamma rays are energy, there's not particles. So release of particles and energy from nuclides, you can say spontaneous release. Spontaneous disintegration of the nucleus, releasing particles and energy. Many isotopes are radioactive. What's the definition of an isotope? That's Gen Chem 1. Right. Atoms of the same element with different neutron numbers. Carbon 14 and carbon 12. Isotopes. One has 8 neutrons, one has 6 neutrons. There's many radioactive isotopes. This shows nuclear binding energy on the left and the mass number on the right. And there is a point of maximum stability here, and that's iron 56. And actually, it's, I believe, that is the highest weight element that is formed in stars, in the actual nuclear process of stars. The other elements that are higher weight are formed in other processes. Okay, and that's because that's the most stable of the nuclides that form. After that, stability goes down. Okay. You notice the big jump in the first one, going from hydrogen to helium. That is the basis for fusion energy, that huge energy that is released in forming that nuclide. So you got this nuclear binding energy, okay, that holds the nucleus together. And the neutrons are partly responsible for that binding, because you know that you've got a bunch of protons packed together. They're going to want to repel each other, right? They're all positively charged. The neutrons mitigate that repulsive force and bind your nucleus together. That's the strong nuclear force, basically. One of the fundamental forces of nature. And as we move down, we get increasing instability. Now, this figure's, I'm not crazy about this figure. I'm used to it, the reverse of this. And that's because I always put the independent variable on the x-axis, okay? And the number of protons is the independent variable, because the number of neutrons is dependent on the number of protons. It increases, right? The ratio of neutrons to protons increases as the atomic mass goes across, as the periodic table increases, right? Because you look at, take a look at calcium, okay? The average atomic mass there of all the isotopes is 40. And it's atomic number 20, which tells you 20 protons, 20 neutrons roughly, right? Now take a look at mercury. The average atomic mass is not 160, it's 200, which tells you there's a lot more neutrons, lot greater ratio of neutrons to protons as you get up. So the number of neutrons is needed to stabilize the nucleus. The more protons you get, a greater ratio of them. Of course, there's more neutrons because there's more protons. So the important thing is there's a greater ratio of neutrons to protons as we move in increasing atomic number. So I like to swap this graph and have the curve go up. It's also confusing by saying it goes to stable isotope curve well beyond 83. Because what do we mean by stable? So someone look at the periodic table and tell me there's a point at which, beyond which, every single isotope of every element is radioactive. That means they're unstable. And what point is that? So if I tell you carbon, some are radioactive, some are not radioactive, right? Hydrogen, some isotopes are radioactive, some are not radioactive. If I told you americium, which is down there at 95, all of its isotopes are radioactive. Same with uranium, 92. So which point does that happen? Does anybody know? You can't tell by looking at the periodic table, you just have to know. Right. Everything beyond bismuth, very good. Cameron, right? Cameron's right. Everything beyond bismuth, all the isotopes are radioactive. Some polonium forward. So this curve's a little confusing, but I think what he means by this is stable isotopes, ones that have really long half-lives, I guess, or the most stable of that element. Because uranium-235, I don't know what its half-life is, but it's not stable. It's radioactive, and it's actually fissionable. So I like this graph, which shows it like this, and also cuts it off at 80. You could cut off at 83 if you wanted. This bismuth is up to bismuth. But then you realize anything beyond that is unstable. And this is basically isotopes, that are not radioactive, but it's showing you at least the ratio and how it changes, okay? So either way, questions? So radiation is split into three components by electrically charged particles. This figure is straight from like a Gen Chem type figure. Original experiments were done with these lead blocks with a radioactive substance. And then beta particles are negatively charged. We can designate a beta particle, with the beta symbol and a negative, or an electron, 0, -1, like that. It is the same as an electron. It's just not derived from outside the nucleus. It is derived from the nucleus. Okay, it originates from the nucleus. Well, how does a beta particle originate from the nucleus? And that's because a neutron will break down into a proton. Whoops, that should be a plus sign. And a beta particle, an electron. That's what happens in the nucleus. It breaks down to that and releases the beta particle. So neutrons, protons are not fundamental particles. They're composed of other things. You all know probably things like quarks and gluons and mesons and bosons and all those things. Electron is a fundamental particle. And an alpha particle is, you can use the alpha symbol like this, or the helium nucleus. It's basically 2 protons and 2 neutrons. Okay? That's what an alpha particle is. So effectively, the nucleus is giving off a chunk of itself to stabilize itself. And in some cases, that's an alpha particle. It's not, keep in mind, it's not helium itself because there's no electrons there, but it's equivalent to the helium nucleus, 2 protons and 2 neutrons. That's all the helium nucleus is. When you think about these particles in matter and you say to yourself, well, how does it give off helium? Well, it's just giving off the equivalent of the helium nucleus, that's all. It doesn't have the electrons that are associated with helium. There's also things like positron emission and electron capture. Your book mentions, I think, one of those. These are just some of the nuclear processes. There's neutron emitters. There's neutron absorbers. Positron emission. A positron is basically a positive beta particle. Electron capture is actually when the nucleus captures an inner core electron and combines with a proton. It's usually a proton-rich type of material element. Captures an electron, converts to a neutron. It's kind of the reverse process of the beta particle emission. There's all sorts of weird stuff like that goes on, these nuclear processes. These are half-lives of some radioactive isotopes. There's uranium-238. We'll talk about that when we talk about nuclear fission. 4.5 billion years. Of course, we can just do the math to figure that out. We don't have to have been around that long to do it. We can just do the calculation, right? And then there's some that are ridiculously short. And because they're so short, they're not included in that average atomic mass up there. right? They can't be. Otherwise, we'd have to change the periodic table all the time because the average atomic mass would actually change as this stuff decayed. So when you see the average atomic masses, those are for the stable nuclides that have half-lives that are, thousands and thousands of years at least. But there's plenty of isotopes with really short half-lives. Some of these are used in medical technology, right? You can take isotopes and treat cancer. You can use imaging, as they decay. You can detect them outside the body. You can get images and things like that. You can use radiation therapy, for cancer treatment, stuff like that. Radon's an important one we'll talk about. There's carbon-14 we use for dating things that were once living. You should be able to do a half-life calculation. It's on your outline sheet. So review that from Gen Chem 1 before you take your quiz. This shows you half-life, and it's important to realize it's exponential because it loses half of the previous amount each time. So the first half-life loses the most. It loses 8 here. And this is phosphorus, P32. This is a radioactive isotope I've worked with. I've worked with P32. I've worked with S35. Is a radioactive isotope. And then the next time it loses 4. Next time it loses 2. So you get the idea that this can drag on for a while. And that's one of the problems with nuclear waste. Because it's half-life the way it works, it takes an awful long time for some of this stuff to decay. Don't forget, this is the first order equation. This is based on natural log of A or C or something like that. CT over C naught equals negative KT, right? That's first order reaction from Gen Chem 1. The natural log of the concentration at time T divided by the initial concentration is equal to negative rate constant times your time. And if you don't know the rate constant, you can get it from this equation, but you have to have the half-life. You have to have one of those. So you can calculate how much is left after 10,000 years if the half-life is, 50 years. All right, this is the kind of ways we did this is Gen Chem calculations. It's something you need to review. We'll do one later on related to nuclear waste decay. Let's talk a little bit about exposure effects to finish up for the day. Ionizing radiation. What's ionizing radiation? Either give me an example of ionizing radiation or kind of define it for me. Yes. Chlorine radicals. What else? Well, no, because that's not radiation. That's an actual particle. Well, I guess alpha particles. Forming radicals. Oh, okay. So forming radicals, right? So dislodging an electron, right? Something like that. I guess energy or particles. We call it radiation, but alpha particles are ionizing radiation. Knock electrons out of atomic shells. Form radicals. What Grace said. So there's gamma radiation. Must be someone else. This is what's happened to me before. I can actually hear my voice now. Someone that has. Is anyone actually listening now? So here we have gamma radiation reacting with water to form radicals. Yeah, there is someone. That's usually what happens. They do something with their system and it comes through when I talk. Okay, this shows, so alpha particles, beta particles, gamma rays, these are all ionizing radiation. UV light, I mentioned this before in the UV section. Most people don't consider it ionizing radiation. It's close, it's right on that border, but it actually can disrupt DNA and stuff, so it's still important. So this is the uranium decay series, starting with uranium-238. The whole half-life is 4.5 billion years. That's what you see here. 4.5 billion years. That's the total time. You notice the first step. This is one that's been delineated. It can take other pathways. This is by far the major pathway. First step takes about 1 billion years, and that's for half of uranium-238 to go to thorium-234. Okay, and that's an alpha emitter. So this is the atomic number on the x-axis, mass number on the y-axis. So moving diagonally down will be an alpha decay, going from 238 to 234 and going from 92 to 90. So since it's 90, it must be thorium. Atomic number goes hand in hand with the symbol of the element, right? So this is a nuclear process, so we change from one element to another. It's the only time we can do this. We can't do this in general chemistry in labs. Otherwise, I'd be up, instead of teaching you, I'd be up in my lab making gold and then selling the world. So we can't change one element to another, and we can't control these processes. They're nuclear processes. We can't speed up the reactions with increasing the temperature. If we could solve the radioactive waste problem by heating them up and getting them to decay faster. It's a nuclear process. We can't do that. And eventually you get to radium and then to radon, and that's an important one that we'll talk about later. Eventually it stops because it's stable. And this is lead-206, and that happens to be a stable isotope. There's a couple other leads that aren't stable. There's lead-214 right there, and lead-210, but they're not stable, so it keeps going. So it goes through these decays, and in the process, it's giving off gamma radiation also. Gamma radiation usually accompanies like alpha and beta decay, and it eventually stops. And to finish up, this is kind of the penetrating abilities of different particles and rings. Okay, so I've worked with alpha and beta emitters, never with gamma emitters. So I can work behind a thick plexiglass shield, wear a radiation badge. This is when I was doing cancer research at Dr. Chase Cancer Institute. I worked with alpha and beta emitters. And they collect that badge every once in a while and, measure your radiation exposure, just like people that work at nuclear power plants, things like that. Okay, good place to start.
All right, so this is what we were talking about, radioactive decay. This is a radioactive decay series right here. And I was pointing out that, in fact, radon is right here. So this is one of the daughter nuclides. We call them daughter nuclides, starting with uranium. For this particular, radium going to radon. So you've got radium right here decaying to radon. And we had said movement like this is an alpha decay. You can see the alpha particles coming off because you're decreasing 2 atomic numbers and 4 mass numbers, because you're losing 2 protons and 2 neutrons, because an alpha particle is 2 protons and 2 neutrons. And then the beta decays would be going this way, and you're adding a proton. Remember what a beta decay is. So I was about to go right on my iPad. Remember what a beta decay is. They used to have, these pens used to work, but they've stopped working. I believe they don't work anymore. No, they don't work anymore. Remember what a beta decay is. Just to do this. So for instance, what's happening with the beta decay? So let's say carbon 14 goes through a beta decay. We notice what happens is atomic number increases by 1, right? Why is this happening? How's this happening? Well, we have a neutron that's actually decaying into a proton and an electron, if you will. Okay, so your atomic number increases by 1, but your mass number stays the same. Mass number stays the same because you've lost the neutron, but you've gained a proton, so the mass number stays the same, but your atomic number increases by 1. That's radon. Of course, we'll talk about that more somewhere. It might be this set of slides. I can't remember. And this is just the penetrating ability, so you get an idea. Alpha, beta, and gamma. So beta particles can be stopped by like a thick piece of plexiglass, something like that. Aluminum foil here. So what does that mean in terms of, biological effects of radiation? So these RENs give you an idea, but they don't really mean anything to you unless you have some sort of context. So one X-ray is about 30 millirens. Okay, and these are in RENs. Okay, and obviously, if you go to the dentist, they put lead blankets on you to protect you. If you're pregnant or something like that, they don't want you getting a bunch of X-rays because this is ionizing radiation. It's dangerous. Small doses is not going to be a problem. Get up to 50, you have inconsistent types of results. Some people might be affected, some people won't, just like anything. Some people exposed to something and have an allergic reaction, others don't, or have a toxic effect and others don't. So biochemistry varies, that's clear. But once you get up into these ranges, then you're going to see people, everyone being affected. And then you get to levels in which you've got problems that are significant. And of course, Marie Curie, who's one of the founders of radiation and isolation of radioactive materials and stuff like that, lost her life to leukemia because of working with these materials without much protection. Back when they would just get big, literally dump trucks loads of ore delivered to them, and then they'd work in their little shack there and separate out the radioactive materials without much protection at all. And they started to realize that as they worked with it and things that they were seeing and happening, that it was, not good to expose yourself to a lot of this stuff. All right, so this is annual radiation exposure in the US. And you can compare this to table 9.4 in your book. The things match up pretty good. I created this pie chart. That's on page 217. And it's got early 1980s and 2006. I don't remember what my date is from. If I had a year and then notes or anything, I forget. But anyway, you see that a lot of it is natural. I mean, this is not, man-made. This is just in the soil underneath your house, in some of the materials used to make, stuff like bricks and stuff like this. So terrestrial stuff that has small amounts of uranium in it. Part of just, and some areas have more than others. So there's areas in the country that are radon hotspots. Tennessee has a few. New Jersey, my home state, has a few. So it's never a bad idea to make that part of either a home inspection if there's concerns, or to at least test it yourself. These little radon kits. They're easy to get a hold of. You simply just open them up and allow them to sit there for a couple of days, cap them up and throw them off, send them off to a lab. They charge you like, I don't know, $50. You get 2 vials and you can put one in your crawl space and maybe one in a lower level of your house if you're interested in how much radon's getting into your house. And have it at least give you some, there'll be discrepancies on what's safe and what's not. The World Health Organization's numbers are different than EPA's, but at least you get a ballpark figure and know if your house is a concern, because it is a carcinogen, radon. It causes lung cancer. Of course, these are man-made, so I've got it divided. I believe that this is all natural right here. If you look at the colors, radon, cosmic rays, terrestrial, and internal. Of course, you all are advanced science students, so when I mention this stuff into my 1000 level courses, or even I teach a non-science major course for honor students, Chem 1030, A lot of them don't realize that we're all radioactive, right? We have radioactive isotopes that are part of the building blocks of life, carbon-14 and all of this, right? So you have internal isotopes in your body that are radioactive. I mean, so biochemically, the body doesn't distinguish between carbon-12 and carbon-14. It doesn't care. It's going to build a carbohydrate with either one. Okay, it doesn't, because that's a nuclear thing, right? So when we think about chemistry, the nucleus doesn't really come into play. It's the electrons, right, that do the bonding and form the molecules and all of this, form the ions. So this is all natural. This is about 50%, and the rest is man-made. And most of this, the average person can avoid. It's people that are more getting a procedure done a lot because they have health concerns or work in the field that have more exposure. There are consumer products out there. So for instance, fertilizer is a little bit higher radiation because of some of the radioactive isotopes associated with elements that are typically in fertilizers. Some of your glassware and stuff like that, because it's got certain isotopes of lead in it. If you've got like crystal lead glassware, I'm talking about. I'm not talking about everyday glassware. I'm talking about like if you've got like, something really fancy and nice. And there's a few other things like that. Oh, smoke detectors, of course, have americium in them as their mechanism for triggering the alarm. But it's not a concern on a daily basis. I mean, it's going to be more than just your background radiation if you were still living in, with running around with spears and stuff like that back when we were, didn't have any consumer products like this, but it's still not a lot of radiation. These are maps of radon zones. You can see Tennessee's got a little bit of hot regions. And heck, I forget what the zones mean. I know the darker one is worse. Let's see if I have another figure. No, I guess I don't. Somewhere I've got another figure. Oh, here it is in your book. That was from your book. Zone 1, counties with predicted average indoor radon levels of greater than 4 picocuries per liter. Zone 2 is between 2 and 4. And zone 3 is less than 2. So it's read in your book on page 216. I missed this here, but it's from your book. I have another one I use for another class. I think it's color coded or something. Oh, so these people that are on Zoom, what's going on for them? They can they? I'm not running. Well, yeah, I am running Zoom, so they're fine. That's right. I've got Zoom running there. I'm just not running on my iPad. Okay, so they're good. And who's that? Anthony and Logan. What's your first name again? William. You're William Rollins, right? Yeah. I was thinking you were Logan before. Okay, Logan's up there. All right, so it's a natural degradation product in soil. You saw that through the decay sequence I showed you. That full figure, cold. Heats all the way up. So here's the step that leads to radon. It's radium, alpha decay, and there's your radon. And the half-life for this step is 3.8 days. Now, the problem with radon is it's a gas. Otherwise, your soil's got radioactive isotopes in it, right? But it stays in your soil. It's below your house. It's below the subfloor, the foundation. No big deal. But the radon's a gas, so that's what allows it to be a problem because now it can diffuse into your house, and now it's in your breathing space. Okay, where the uranium and the radium, which are radioactive, are still in the soil. So, if you have a problem with radon, I've actually heard scientists say this. It wasn't their particular area, but it said you can just put down, the film that you put down in your crawl space for humidity. It's thick plastic stuff that just lays on the ground, and that'll solve your problem because an alpha emitter can be stopped by that. And that is correct. The problem is not here. The problem is here. That plastic's not going to stop the radon from getting into your house. It's the gas. It's going to diffuse right around the gaps and Gases can even diffuse through plastic, depending on the plastic. Still going to get into your house plenty easily. And then the half-life of this is 3.1 minutes, and this is a solid. Okay, you should know that because it's polonium. It's a solid. You know the gases on the periodic table, hydrogen there, and the only two liquids are mercury and bromine. So polonium's a solid. There's the problem, because you breathe in the air in your house, the radon comes in, and now it quickly so you've got half-life only 3.1 minutes. So some of the radon is forming particles that now are in the air that are adhering to your alveoli and stuff like that and trapped in your lungs. So because keep in mind, 3.1 minutes is a pretty long half-life when you're talking about breathing in and breathing out. How long is the air in your lung? 15 seconds, if that. So that's not a problem. The problem is this gets trapped in the lungs now because you've got these particles now, and you've learned about, small particles. We talked about particulate matter, stuff like that. But this can now be adhered in the lungs, and then it sits there because it doesn't get exhaled anymore and goes through radioactive decay because this is radioactive. Okay, so that's where the problem comes from, is from this. So the plastic in your crawl space doesn't really help. People that really mitigate radon in houses will put in ventilation systems. So they'll put in actual fan systems if you have a real bad radon problem and exhaust it, and it will stay there all the time. It'll just run periodically or something like that. If it's not that bad, just being prudent and opening up vents underneath your house, airing it out, airing out your house and things like that. We live in a society nowadays where lots of times people go from air conditioner to heat, never open their windows. I hate that. I'm the type of person that barely ever uses air conditioner. My house, I use it in the summer, of course, but my car, I always open my house and air it out. I just like fresh air. But if your house is closed all the time, and a lot of buildings are closed all the time, the way they build them nowadays, you don't have windows that can open. I can't open a window in my office. So depending on what your levels are, in some cases it's bad enough that you have to have it mitigated and actually have to have a ventilation system put in. Questions? So let's do an example problem here. This is real easy. Strontium-90 is a byproduct of nuclear testing. If it undergoes beta decay, what is the daughter nuclide? So figure it out and raise your hand if you've got it. Shouldn't take you but a minute or two. Anybody? Yttrium-39, correct. Pretty straightforward, right? Beta decay. Okay. I gave you something, and I gave you a couple in the quiz, didn't I? I think I gave you maybe a fission one and asked you to predict the daughter nuclide or something. I can't remember. Maybe another one. I can't remember. All right. All right, let's do now a half-life problem. Plutonium-239, which is a problem, as we'll start to talk about nuclear waste today. We'll talk about things like Chernobyl. Has a half-life of 24,400 years. This is one of the problems with nuclear waste, is a lot of the radioactive isotopes have really long half-lives. And it takes them years, because it's exponential, right? It takes them years before they're safe to be around. So they have to be stored for thousands of years. This is the big problem with nuclear waste. If a particular nuclear weapon site is contaminated with this isotope, and safe levels will not be reached until the isotope's activity is at 0.0977% of its current activity, how long before the site is safe to occupy? a very practical question. You've got radioactive materials there. And this is what they calculated when they decided, okay, how long it will be before Chernobyl will be able to be occupied. This is a first order rate equation. You should recognize it. Nuclear decay is first order. First order is a great rate equation to be familiar with because it applies to a lot of things. Okay, it's a very useful equation. Radioactive decay, even things like pesticide decay in the environment, stuff like that, often follow first order kinetics. And you have this equation too. This can be derived, if you will, if you're not comfortable, the type of person that gets handed an equation, want to know why that works or where it comes from. This can be derived by just plugging, 1/2 of C naught into here and solving for it and taking the natural log of 1/2. That's where the 0.693 comes from. You don't have to be able to do that, but I don't like to just sometimes throw something out there and not explain where it comes from. Okay, so you can derive this equation by simply putting in here 1/2 of C naught and C naught, because that's what half-life is, right? And you just solve that. Okay, get rid of the CT, get rid of another variable. You solve for T, 1/2 in terms of K, and that's where the 0.693 comes from, because the natural log of 1/2 is 0.693. It's negative 0.693, but then you got the negative here. So how do we solve this then? We're interested in knowing what? How long, right? T. So what am I going to do? Okay, so clearly I've got a half-life, right? So I can clearly just get my K, right? And then I can plug my K, or I can just plug this right into here and solve it in one step, or I can get my K and plug it in. Doesn't matter either way. Question is, what's going to go here? Yeah, so what number actually? No, very good. Amal wants to put this over 100, and that's exactly right. This is the concentration at time t, or activity, same thing. You can do it in terms of concentration or activity. Activity, you're just measuring with like a Geiger count or something like that. Over 100, because that's a percentage. We don't want it in a percentage. We want it in a fraction. It's just right on target there. And then we just solve that. So I forget how I did it. I guess I put it all into one. There's my natural log and did what Amal said here. And then there I've just substituted in here. There's the negative that's still there. And I just said, okay, I don't have K. So that means K is 0.693 over T 1/2 times T. And then it becomes over 24,400, because that's my T 1/2 times T. And then solve for T, take a natural log of this, divide by that, you get 244,000 years. Okay, that's the problem. Okay, we've got 250,000 years before it's safe to occupy. Questions? Okay. So it's a nice application of general chemistry. That's what I like to do in this course, just kind of because it's introductory, even though it's a 4,000 level, it's introductory. Take Gen Chem and apply it to environmental stuff. Some people might recognize this approach. 0.5 to the n is the fraction remaining, where n is the number of half-lives. I don't buy it. Comes more from biology when they use the exponential growth or whatever like that. I just default to the first order rate equation all the time because I know that it's not hard to do. Just plug in there and use that. But you can derive this the same way from these. So let's talk about fission and fusion. We're going to have a presentation on fusion before too long. I'm going to spend most of the time talking about fission and leave fusion, except for some basic stuff. They can cover it too. Just because I cover it doesn't mean the fusion people can't cover it. But I don't know what they're going to cover, so I'm going to cover some stuff. But I try not to do too much when someone's doing a presentation. So fission of uranium-235. This is uranium-235 right here. fission needs to be initiated with a neutron? That was one of the questions, I think, on your quiz related to radioactivity and fission, the differences or similarities, something like that I asked. It forms this unstable, this is already unstable, but even less stable, and then it splits. And of course, you know the history of this. I'm actually going over fall break out to New Mexico for a short trip, and I hope to go to Los Alamos. So Los Alamos, of course, was one of the 3 secret installations that the U.S. established in response to building the bomb and in response to Germany at this time. Of course, we go back to the 30s. Germany's conquered Poland, Italy's in line with Germany with Mussolini, who's fascist. So scientists had realized what some German scientists had done, what they did with their experimenting, and what's unique about this, radioactive decay gives off a small particle, right? An alpha particle, beta particle, or gamma rays. This is literally splitting the nucleus. And we know from Einstein's E equals MC, well, no, not from E equals MC squared. We do matter and energy are interconvertible, but we know that there's a mass deficit, actually. If you add up all the protons, neutrons, and mass of an atom, there's a deficit there. And that's because it's converted to energy. And that energy is what binds the nucleus. That's the nuclear binding energy. Tremendous amount of energy was released. Strassmann, Otto, I can never remember the third scientist's name. The 3 scientists in Germany that were working with this stuff. So you had Enrico Fermi in Italy, who's a nuclear physicist also, that realized what they were doing. And some scientists start to be concerned because of what was going on in the world, of course, that this could be developed into a bomb. So they needed Roosevelt to listen. And the best way to get him to listen was to just call on the most famous scientist in the world and get him to write a letter. And that's what Albert Einstein did. He wrote a letter. Roosevelt listened and established the Manhattan Project. And of course, we have one of the secret installations in our home state with Oak Ridge. So you have Oak Ridge in Tennessee, Los Alamos in New Mexico, and Hanford in Washington State. Hanford is considered by some people the most polluted place on the planet due to all the nuclear weapons over the years. Maybe Chernobyl's worse, I don't know. But Hanford, before Chernobyl, was considered one of the worst. And those different installations had different jobs. One of the keys to this reactions, which I'll talk about in a second, is it's producing more neutrons. That's what creates the chain reaction. So each of these can now go split another uranium-235. Now look at your periodic table and make an educated guess for me what the major isotope of uranium is. Or if you know, just say it. But if you had to guess and didn't know, what would you guess? Doesn't necessarily have to be correct, but if you had to make an educated guess, what would it be? This is the average of all the isotopes, right? So major isotope of calcium is 40. So you might guess that it's what? 238. Doesn't always work, right? Because like look at chlorine. It's got 2 isotopes of 35, 37, the 2 major isotopes, right? So you wouldn't know by looking at that necessarily, but lots of times it does work because there's one major isotope. Carbon's major isotope is 12, and that, therefore the mass is right at 12, right? The other ones are minor. So the major isotope of uranium is 238, but we need uranium-235. Why? Because this one is fissionable. 238 is not. If you bombard 238 with a neutron, it does not fissile like this. Okay? So this only represents 0.7%, I think, of all the isotopes. Most of it's 238. To make a bomb, you need 90%. So you have to enrich it. Okay, so you have to take it from 0.7% and get it up to 90% to effectively make a bomb. You have to have enough fissile material. You're talking about something like a softball in terms of actual size. Don't quote me on that, but it's not, it's not far from that. Mass, that's important, obviously, than size, but I'm just, Here's your nuclear chain reaction showing the other neutrons. So this is just a figure from your book. It's really not much different. This just means fission product. Equation 9.5 shows you one of the nuclear equations that can result from these bombardments and splittings. And it's producing barium and krypton. It's on page 220, and 3 neutrons. So these equations are balanced, okay? So you can effectively, I had a better pen. That thing seems so light that I wrote with. Yeah. Oh, they are. Okay, hang on. Let me see the chat. Thank you. 230. Okay. We can see everything. Thank you. 238. Correct. All right. Yeah, I kind of forget to use that. So these equations are balanced, just like radioactive decay equations. So, and I'm just going to make one up. This might not be a real fission equation. I just want to use something different than the book. But if we had, so your uranium-238, oh no, not uranium-235-92. Am I on the screen here? And let's just say we get, I just don't want to use the same one. Barium-140. I don't even know if that's barium-140. Barium's atomic number is what? 56? 56. I can look at that one as close. 56. And let's say it produces 2 neutrons. What's the other daughter? Right? And you should be able to figure this out. That's all. So we just have to take 235 minus 140, and this is 2 minus 2, and then we can take the bottom, and it should be what? 36 for the bottom, right? So that means it's element what? Krypton, right? And someone get me the top number. Was it 235 minus 140? So that's 95. And then minus 2 more, right? Because you got minus the 2 neutrons, right? So 93. So we get 93 up top, and that's your daughter, the other daughter nuclide. It's very similar to the one in the book. I just chose, barium just to make it, but you don't have to get barium and krypton every time. So these are all balanced. Now, so Oak Ridge's job was to take uranium-235 and enrich it. And back then we used gaseous diffusion. Now everybody looks for centrifuges. So uranium-235 and 238 have different masses, right? So you can centrifuge, use specialized centrifuge, and separate them out. Okay, that's why we look for centrifuges now. But we used to use gaseous diffusion. And what Oak Ridge did was they converted. I really wish I could write here. That's why I use the iPad. What they did, Oak Ridge, was they converted the uranium. It comes in like uranium dioxide, but they converted the uranium to uranium hexafluoride, which is a gas. And then they use these gaseous tubes. And you learn in Gen Chem that what's going to move faster, hydrogen gas or carbon dioxide? Not a trick question. Which one's going to be faster? What's that? Hydrogen, because it's lighter. You learn that from laws of diffusion and effusion, right? So uranium-235 hexafluoride will be faster than uranium-238 hexafluoride. So what they do is they use these large tubes and they collect it and they kind of like filter, I don't know exactly how they do it and the intricacies of it, but basically they collect a proportion of it that comes off the tubes, and the real slow stuff they don't collect, and they keep doing that repeatedly over and over, something along those lines. They're really long tubes. I don't know the intricacies of it, but that's the concept behind it, is you enrich it that way by weeding out the slowpokes, for lack of better words. And then they convert it back to uranium solid, like uranium dioxide, and pack it into pellets, which go into the rods if you're building a nuclear power plant. But for nuclear power plants, you only need 3% enrichment, not 90%. So you can't take the nuclear material from a power plant and make a bomb out of it. That's what, people used to make that observation or statement back when, we had issues about people trying to get a hold of materials, groups of people we didn't want to have it, or something like that. So, but you can't just take it from a nuclear power plant. It still has to be enriched. The only thing you do with that is make a dirty bomb. Yeah, I know. That's the way the camera's set up. I can't do anything about that. I don't know why they do that. They show like half of each board. It's bizarre. Look at that. And it's idiotic. You don't need to show both, really. You should just put the camera on one. I guess you do, though, because sometimes people write on one of the boards. But what the heck good is that, I guess? Anyway, sorry about that. Yeah, that's why I don't use this system. It's fine in my other classroom. So you only need 3% enrichment for nuclear power plant. So this is just fission at a controlled rate. The bomb is allowing it to basically just go out of control. You're using a critical mass in which all the neutrons are captured and split additional uranium, and that creates this massive chain reaction. Where here, you're using control rods, which absorb neutrons. So certain materials can absorb neutrons, and we use those as control rods. And if we absorb the neutrons, the reaction shuts down, right? Because that's what's causing the fission. So that's the whole idea of the control rods. But otherwise, the mechanics are pretty straightforward. It's like burning coal or anything. You're just using steam to turn a turbine. And you got some cooling water. So you do get some thermal pollution because the water you're dumping into the nearby river, this is why power plants are always next to bodies of water. That water you're dumping in is typically about 10 degrees warmer. So that creates a problem for some organisms. But there's no real water pollution other than thermal pollution like that. It's a pretty clean system. This is contained, right? So it's not like this water is radioactive or anything. This is all contained. Okay, and this is water in here as a moderator. The moderator will slow down the neutrons, because if the neutrons are not slowed down, you don't have effective fissions. They're moving too fast. So what you have is, I'll show you in a second, you have natural materials that emit neutrons. Okay, so you're going to pack those in there. Okay, and then they got to kind of slow down the neutrons to get the fissions to be effective. There's a lot that goes into it. Eventually, these rods have to be changed out. Just depends on the design, type of reactor. Every 1 to 3 years, that material becomes waste that has to be dealt with really long half-lives. Every time I touch the Zoom chat, I've got to remember to re-click PowerPoint. So this is some actual figures. These things are just steam towers. Okay, people see this when they drive by nuclear power plants. Oh, they're giving off radiation. No, radiation is contained within these buildings, usually right here. There's your individual pellets of uranium, and here are the rods they're packed into. It shows you kind of the core area. This is just another schematic showing it. There's nothing much new here. There's the system there. There's the steam being converted, turbine, water vapor. one's a little bit more detailed. Fuel handling area, concrete shield building. You can have all concrete here, steel, concrete and steel containment. So these cooling water tanks, these are emergency like cooling tanks that you saw like here. Steam generators, reactor coolant pumps. Oh, that was the cooling. There's the cooling water up there. Passive containment cooling water tank. These are steam generators down here. Reactor vessel. Didn't realize it's just the scale of this figure. It looks like these things are so close to the core. I don't know what that is. Pressurizer, main control room, speed water pumps, turbine generator. So this shows you, and I think I'm going to need someone to remind me in the notes there. The black ones are your actual fuel rods. And Amal, what does it say? The green are and the oh, okay. There you go. So not many of the startup neutron sources. How come yours doesn't have it and hers does it? Okay. So you're packed with neutron sources, and what were the other ones you said? Which are the control rods? Okay, different types of control rods. Okay, and so there's certain materials that naturally absorb neutrons. One of them is boron. One of the isotopes of boron, cadmium. I think they use. So there's different types of materials that will absorb neutrons, and they can lower and raise these to control the reaction. These are nuclear power plants in operation in the United States in 2008. It hasn't changed, so I don't need to upgrade this. We haven't really brought online anything new. Most of these power plants are old. A lot of them are past their kind of like their suspected plant life, which is a bit of a concern. Materials start to get brittle when bombarded with radiation over time, and they can become radioactive. Parts of it, it's low-level radiation. But when you dismember a plant, a lot of that stuff is low-level radioactive waste. The core stuff of all of that is high radiation. Of course, Tennessee's got two. This is nuclear share. So we're right about for electricity, right about 20% the United States is. France uses a ton for their electricity, 3/4, but they use less than us because they're a smaller country. Even though they're getting 75% of their electricity from nuclear, and they have a lot of problems with nuclear waste disposal. They're trying to ship it places, and a lot of countries are now saying no. So that's one of the big problems. Belgium, 50%, Hungary. So, a couple terms, some of which I mentioned, some maybe I didn't. The critical mass is the material you need. So, the first sustained nuclear reaction. So Enrico Fermi went to Sweden to accept his Nobel Prize, and then he defected to the United States. They set up a lab in an old indoor tennis court in the basement of like University of Chicago, and that's where they had the first sustained nuclear fission reaction. And the key is getting that critical mass so that enough neutrons are absorbed to maintain the reaction. So that's the difference between a power plant and a bomb. A bomb, you want to absorb like all the neutrons, right? So you get a tremendous amount of energy. A plant, you want to just kind of like have that steady state where you absorb enough neutrons just to keep it running, basically. The moderator, as I mentioned, slows down the neutrons and makes the fissions more likely, more probable. We already know what control rods are. We talked about isotopic separation. Breeder reactor produces a fissionable material, plutonium. So certain isotopes of plutonium are fissionable. Plutonium really doesn't occur naturally. Nothing after uranium really occurs naturally. Everything else beyond uranium up there on your periodic table, and these periodic tables stink. I hate them, but anyway, they've got lanthanide and actinide down here instead of up here, which messes up all your electron configuration stuff. Because now you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 instead of 14. And you all know there's 7 f orbitals that hold 14 electrons, so that messes with everybody. And they're in the Gen Chem classroom I teach too, 2006. But anyway, everything beyond uranium is synthetic. Okay, it doesn't occur naturally. So this will form in a breeder reactor, and that is fissionable. So it creates a fuel. So effectively, by running a breeder reactor, you're actually creating some fuel also, which is good. You can read a little bit about the thorium. Thorium has some advantages. And it's at the end of the chapter, I believe. Yeah, has some advantages. Some people are pushing to use thorium more. Yellow is more abundant, exists almost entirely as a single isotope, so enriching it's much easier. Its half-life is over twice as long as uranium-238, so that makes it less radioactive. So there's different things. You can just read on page 234 about thorium. Reprocessing is this whole process here. Oops. It's on page 232. Figure 912. I have it somewhere, but I'll talk about the reprocessing in a bit. Hang on to that. I'm not going to say much about it. I'm just going to describe the figure that's in your book, but just show you at least a little bit about it. Let's just look at problems with fission power. You've got to mine the isotope. It's got to be processed, and then ultimately, unless you're going to have all this nuclear waste, you got to reprocess it. And that's this reprocessing here. And even when you reprocess it, that doesn't solve the problem. It just allows us to get more energy out of it and reduce our waste. Accidents, the ones you know, 3 Mile Island, Chernobyl, and Fukushima. 3 Mile Island wasn't particularly bad. Very little radiation released. Of course, it was the first one. We're talking what? 70 something? 79? Thank you. I was going to say 79, but I wasn't sure, so I held off. Not a lot released. Human error was pretty well contained. Chernobyl, environmental disaster, of course, one of the worst environmental disasters we know. And let's talk about Chernobyl here in a bit. Fukushima, you know, unfortunate. They're actually pretty well designed with backup systems. They had like a 30-foot wall to protect against any waves. And of course, the tidal wave was 33 feet. The water gets in, knocks out, you know, backup generators and all this. Systems shut down. And then you get things like explosions, because one of the things you have is uranium dioxide is coated with zirconium. And most metals, and it's atomic number 40, most metals, when exposed, you know this from Gen Chem, to like acids, right? Produce like hydrogen gas, but even high temperature steam. That's what happens. High temperature steam reacts with the zirconium coating on the rods and produces hydrogen gas. And then that, of course, is flammable. We'll know what happened with the Hindenburg. So hydrogen gas is not a, you know, that's one of the big problems with hydrogen as a fuel. That's what happens. So then you have explosions, and that's what spreads the isotopes. See, with here, no fires, no explosions, radiation was contained. Chernobyl, problem, because it caught fire and you had explosions. And there's still debate about, theoretically, what actually happened, whether it was hydrogen gas produced or if it was the graphite, which I'll talk about here. So human error during test procedure, they were switching shifts. And the night shift or the day shift, I don't remember, was shutting down some safety systems to run some tests. But that was never communicated properly to the other shift. So they started doing stuff or running some stuff that shouldn't have been because certain systems were shut down. Ultimately, they used graphite as a moderator in the former Soviet Union. So this was in basically Ukraine. What we have know is Ukraine now, the former Soviet Union. They used graphite as a moderator instead of water. Graphite has some advantages. It's a better moderator. It does a better job at slowing the neutrons, gives you better collisions, more efficient collisions, but it's flammable. It's carbon, okay? And that's what happened. It caught fire. That would never happen with the designs in this country because all of our moderators are water. You're not going to have that type of problem. You could still have, I don't remember with Fukushima, if they use graphite or just water. I think they use just water. You could still have problems with the hydrogen forming, but this is believed to be one of the problems for sure. And they result in what's called a positive reactivity coefficient. And this goes by a couple different names. It's also, well, it's a reactivity coefficient, but they also call it a reactivity void or something like that. It has to do with, I don't really truly have a really great understanding of it. It has to do with the steam and the amount that evaporates and how much space that creates and how that affects the reaction. I don't know, but this resulted in a positive reactivity coefficient, accelerated the reactions that led to the problem. So it says the reaction speeds up when power levels dip very low. That's a little confusing. It's because more steam is produced as temperatures increase, there's more boiling, but the actual power level of the reactor drops, or something along those lines. It's a little confusing. 31 acute deaths, up to 1,000 others with acute radiation syndrome, over 350,000 people evacuated and resettled. Increase in thyroid cancers among children. Why thyroid? Same thing with Fukushima. Why thyroid? Anybody know? Right. Right. So iodines collect. Thyroids use iodine to make hormones. And one of the isotopes we see from decay and nuclear reactions and accidents is iodine 131. And there's I think there's more than one actually. That's the same type of thing we use for like radiation therapy. So you can get injected with iodine 131 if you have thyroid cancer. The iodine gets selectively drawn to the thyroid because it takes up iodine, doesn't care if it's iodine 129 or 131, and then the radiation kills the cancer cells. So that's what you're doing. You're allowing the thyroid to collect it. But of course, when people are exposed to it in areas where there's accidents, then you have increased thyroid cancers. So it's kind of a catch-22, right? You're using it to treat cancer, but it can also cause cancer, depending on how you're looking at it, right? Animals contaminated above self-safe consumption levels. Difficult to gauge the full effects. So people do this stuff. They make, epidemiological estimations based on, a nuclear reaction or accident or something like that. 4,000 predicted deaths, 20,000 years before it's safe to inhabit. There's actually been some allowance of people to go back into the area, I think for study purposes and things like that. And there were some, I think, local residents that, I don't know, I remember reading something which seemed odd, but were allowed to like at least go back and I can't remember. I remember thinking something weird about why were they letting these people back so soon. So these are pictures. And you might think these were taken right after the disaster, but you know by my last slide, if you have it in your slides, I forget, that these were taken 28 years after. one of the other problems too is the life of the plant. I don't mean green. I'm sorry. Yeah. 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 No, I haven't yet. Yeah, I plan on watching it. It's on my list. I watched the one Manhattan where they made a show on the Manhattan Project. A couple seasons of that, and then yeah, Chernobyl. I forget, was it the HBO show or yeah, I was waiting for it to be released or something on Netflix or something like that. Did you see it? Curious if it's yeah. Yeah, I heard that the reviews were really good. I can't remember if they said that, it's a good depiction historically or not, and what was happening. But yeah, I'm interested in seeing that definitely. So what I mean by plant life is the actual nuclear plants, not green plants. um, they're really expensive to build, and then 50 to 100 years is about the max life of these plants. So, and there's not a lot you can do because it's been bombarded with radiation. It's not like simple infrastructure upgrades for like a coal plant or something. It's a little bit different. All the materials become compromised and have low level radiation. So the rods have to be replaced every 1 to 3 years, depending on the design, 50 to several hundred rods, approximately 250 uranium dioxide pellets per rod. You're looking at 200 to 450 kilograms of uranium dioxide. Plutonium-239, that's the isotope that's made in the breeder reactor. I think I said 244, but that's not right. That's the major isotope of plutonium, but I think it's 239. So you get uranium isotopes, you get barium, krypton, strontium, and cesium, and actinide compounds. So what happens is lots of things happen. You absorb neutrons and you don't fizz. So you form like different types of actinides, okay? And then some of the uranium doesn't fizz, period. So you're left over with some uranium-235. And of course, you have the uranium-238 that can absorb neutrons, and that's not fissile. So you have all these types of materials that are radioactive, and then you have decay products that have long half-lives. So you have all this mixture of different isotopes with different half-lives that create a problem in terms of nuclear waste and how you dispose of it. The rods are cooled above ground underwater. They go into dry storage in concrete canisters. You can reprocess the uranium and plutonium. We currently do not do this in this country. Radioactive liquid is solidified in glass and then put into metal cylinders. So Oak Ridge used to do this. So what you do is it's called like vitrification. So you put the liquid nuclear waste, you add a bunch of like materials that you would use to make glass, like different earth materials like silicon dioxide and minerals and stuff like that. You put in these electrodes with a bunch of heat running through it, voltage running through it, and it forms like a slab, like a glass slab. So they're called vitrification or glassification. The reason they do that is because liquids are much more prone to leak and get into groundwater. So if you have a solid block, it's a little bit better to store. And this, of course, is what Yucca Mountain was supposed to do, was take a place for all of our waste and store it somewhere. That's the big repository in Utah that we put billions of dollars into building and decided, bad idea. And now it's just a big, huge, expensive hole. But the idea was to collect the nuclear waste from all over the country in Hanford and Oak Ridge, Los Alamos, and various other places, and store it all there. But geologists are concerned that you have to store it for so long that you can't guarantee the geological integrity of the site. And if you have seismic activity, earthquakes, things like that, this stuff can wind up all in the aquifers. And then once you contaminate your aquifer with radioactive liquid, forget it. It's unusable for thousands of years, your water source. So right now it's still spread all over the country in various forms like this. So needless to say, I'm not a big fan of nuclear energy because even though it's got no CO2 production, there's really no solution. Remember, this is nuclear. We can't go into the lab and come up with ways to heat it up and get the half-lives to move faster, right? It doesn't work that way. It's nuclear reactions. It's not just chemistry. We learn in chemistry, yeah, temperatures increase the rates of reactions, not for nuclear reactions. So here's the dotted part, is the part that the US does not do. That just stands for light water reactor, which is just your standard, some people use deuterium heavy water reactors. Your standard water reactor that we saw a figure of. But the dashed lines are what we don't do, and that's kind of what we want to be able to do, at least. Take some of this waste, reprocess it, use the fuel. That'll cut down on CO2, not build any new reactors, but there is a push for that. There's these smaller modular designs, supposed to be safer and all that. But nonetheless, you still got to strip mine the ore, which is not going to be super abundant for that long. And then you got to deal with the waste. This history of global nuclear reactor design and construction. And you can see we had our peak. So the gray is number of reactors under construction. And then, so there was the one in Tennessee that was like literally under construction for like 20 years. Was that Watts Bar or was it another one? It was under construction for like 20 something years and eventually came online. I don't remember which one it is. The only one I know the name of is the Watts Bar one.
This is one type of fusion reaction. And you can see, oops, sorry. You can see when you look at this reaction, it's very different than a nuclear fission reaction, right? And it's different than a radioactive decay. Radioactive decay, we see a nuclei giving off a small particle. Nuclear fission, we see a large nuclei splitting into two big chunks. Here we see two small nuclei forming another slightly larger nuclei. Okay, so you got two hydrogens fusing to form helium. And this produces a tremendous amount of energy because of that strong nuclear force, that energy, that binding energy we talked about. And I think we saw it in our isotope figure, this in your book. And this is one of the main reactions that powers our sun, star. And you can see a neutron is released also. Now, there's no practical fusion yet, of course. It's just right now experimental stages and things are still being worked out. But it has lots of advantages over fission if it ever does get worked out. You get more energy, a lot more energy. The reaction is considered somewhat clean in the sense that we don't get a ton of high radioactive nuclides as waste products. Okay, you'll have some small half-lives and smaller nuclei of radiation, but of radioactivity, but nothing significant. So people consider them so much cleaner reactions. You have to deal with the whole nuclear waste process. Very little amounts of material. Reactions are fairly safe in that it doesn't have the potential to get away the way a nuclear fission reaction does. Because basically, if anything goes wrong, the plasma is going to shut down. It's not like it feeds itself and you can get into that reaction running out of control. Because with fission, you realize if you don't absorb enough neutrons, it's turning into literally like a bomb, right? Too many neutrons being absorbed, too much fission going on. Here, you're doing everything possible to contain this thing, to get these things fused together. Extremely difficult engineering wise. And as soon as that containment breaks down, the plasma breaks down, the system just shuts down. The reaction stops. So we're putting in, kind of setting up a system to get this to like fuse. We're going to have to use super high temperatures. We're going to have to like build these special containment type of facilities. And we're going to have to work out all the problems with it in terms of the plasma density and the containment and the plasma fluctuations. So the plasma is very difficult to control. Just imagine basically you're creating kind of like a a sun, a star in a chamber on your planet. So it's a little bit difficult to deal with engineering wise. There's abundant fuel and it's fairly inexpensive to obtain, and I'll elaborate on that. So the problems or the concerns or the limitations are the temperature, controlling the thing. That could be, I got temperature control, but I really want to say, the temperature, we're talking about millions of degrees here, and then controlling that plasma and the cost. It's really expensive right now because of the engineering logistics, of course. So, don't quote me on this, but it's something along these lines. So there's enough deuterium. That, of course, is deuterium. The other one is tritium, right? Two of the isotopes of hydrogen. The main isotope of hydrogen, of course, being protium, which is that one. That's the most abundant one by far. It's a little slow on the delay. But deuterium, it's been estimated there's enough deuterium in life, and once again, don't quote me, but it's something like the top 2 inches of like 2 of the Great Lakes or something like that, or Lake Erie or something like that, to equal all the oil reserves in the world in terms of the amount of energy you get out of that deuterium. Okay. And you can Google something and read about it and maybe correct me on my analogy, but it is something astronomical like that. In that, because the reactions are so darn efficient, you get so much energy out of them. So you don't need a ton of material. Okay. So that's the idea, is we got to work out the engineering part of it. We have plenty of deuterium to run these. Now, this is from your book. And that's the one we just saw right here, deuterium and tritium, this first one. And you look at the temperature, 200 million degrees, 1 to 200 million degrees. I think the tokamak reactor is running at like 200 million degrees. That's what it's kind of set up to do, reach those temperatures. Well, there's other reactions or possibilities to deuterium. You get different temperatures that are needed, and you get different products. But in general, they're small nuclei that fuse to give you a slightly larger nuclei. That's all. And the main ones we're working with right now are 1 and 2, from what I remember or believe to recall. And I forget what the number in the parentheses are. Numbers in parentheses are the energy of the product particles in units of 10 to the 7 kilojoules obtained from the fusion of 1 gram of reactants. Now you see there's 2 lithium ones at the bottom. And this becomes important because what we can do is, well, I'll go there in a second. This is just a picture of the tokamak reactor. So the plasma of the tokamak reactor is contained in the tunnel inside the donut-shaped magnet. So they use magnetic materials. So basically, when you have a plasma, there's not a lot of plasmas, remember. There's stars or plasmas, fluorescent light bulbs. There's a fluorescent up there, I believe. Or plasmas. We used to make plasma TVs. Those are kind of gone by the wayside. But they're highly charged particles, right? High energy, and they're charged. So we can contain them with a magnetic field. And that's the idea, is because they're charged, we can use a magnetic field to contain them, control them. So this is this is known as magnetic confinement. There's also inertial confinement, which we'll talk about in a second. But this is the tokamak reactor. An actual picture of it rather than a schematic. I'm sure we'll hear more about some of the stuff in our presentation. So we need temperatures around 200 million degrees C. Atoms exist as charged species, so we can control that with a magnetic field. The plasma remains suspended. And that's the key, because of these temperatures and the energy of this plasma, you can't have it touching walls and things like that. But we still have to build a containment facility for it, but the plasma is actually suspended during the fusion process. And what they do is this tokamak reactor, they put this lithium blanket. And the reason they do this, because it produces tritium. So these are 2 reactions that show you that tritium is produced. I think I have it highlighted. tritium is produced when it fuses with these two lithium isotopes. And that's obviously a fuel. If you go back and look at our reactions, tritium is one of the isotopes that's used in that first reaction. I guess it's only the first reaction that uses tritium as a fuel. And that's the one that's got the lowest temperature. So if you put a lithium blanket around this thing and absorb those neutrons, you produce a fuel, and then you get a little bit of helium gas as your byproduct that can be a little bit radioactive. I forget about, maybe we'll learn this in the presentation about like some of the radioactivity waste that you have to deal with the fusion. So we've got Cameron, right? Is in this group. Who else is in it? What's your first name again? What is it? William. I cannot remember it. William. And who's your other group member? Sarah. Oh God, she hasn't been here in ages. Is she in touch with you guys at all? Okay. Yeah, well, some people are doing it by Zoom, which is fine, but she's never on Zoom, I don't think. So he's Anthony on Zoom. All right. So with this lithium blanket, we're producing tritium. So, and you guys can clarify this for me also too. I believe the break-even point was theoretically reached back in 2014, but then I think they backpedaled on that because not too long ago they talked about the break-even point being reached again. Break-even point meaning we're getting out as much energy as we put in, which obviously is the key point to get to. It's not a fuel or it's not an energy source until you start getting more energy. But that's where we're at with this. Is we're just at the point of, okay, we're getting out as much energy as we're putting in. So we have to get to the point where obviously we're getting a lot more energy out. So this International Thermonuclear Experimental Reactor, ITER, is got a really cool site. And I'll just click on it, see if it works, but you know, you guys can check it out too for your presentation. Oh, longer than expected working on it, yeah. Skip verification, I've been there numerous times. So that's pretty cool because you can actually do like a 3D walkthrough, a virtual walk, and see different stages and all that. And you know, they got frequently asked questions, but they've got some pretty cool stuff. They got some science section here. You can look at certain things. But let me see if I can quickly just find. They do a progress thing too, where they show you the different. Oh, here we go, right here. So this is one of the things here, which is pretty cool. You can look at the magnets and it explains it. You guys can use this as part of your presentation or get some information here, but it's pretty cool for anybody to look at, not just people giving the presentation. Got a lot of information. So this is one of these international group projects where a lot of countries are involved, the US being one of them. I think it's, where is it, in France, I believe. Somebody asked me, I think, sorry, Sarah, she asked me about the presentation, about a video. And you can use a video, don't make it a primary source, the one that you're going to submit to me, you can use it. I've had students show like a short little video as part of the presentation. If it's like 1 or 2 minutes, they want to make a point or something like that. But obviously, you're not going to show a 20-minute YouTube video. And it can certainly be one of your sources, but you got to make sure you have some good sources other than just, you know, watching videos. All right, so here it is. Here's schematic from your book also that shows that lithium blanket. Pretty simple. So we got seawater coming in. We can separate out the deuterium because obviously anytime there's water, there's going to be deuterium because that's a hydrogen isotope. Separate that out, feed it in and inject it. And then I guess you got to have some tritium to start your reaction up. And then eventually you produce the tritium. So you just cycle that back around. Chemical separation, helium is off. There's a standard turbine. I don't know why I'm pointing up there with my hand. I have an iPad in front of me. There's your standard steam generation there. Same way you would do it with coal or anything like that. And over here is just a blow up of the donut shaped chamber. Okay. Questions? Like I said, I'm gonna leave. Yes. It's a good question. I mean, there's no reason you can't also get it from seawater, but I'm just not sure if the levels are and how much it would take. So that's a good question. If where they get their initial source of tritium, so like the and they probably do the same thing. It's just isolated from seawater, but I'm not positive, so I'll try to check on it. Other questions? So this is an inertial confinement. So this is a little bit different than magnetic confinement. They used a bunch of lasers for this. So powerful laser beams are focused on a tiny frozen pellet of a mixture of deuterium and tritium. The high pressure and temperature causes the hydrogen to fuse. In fact, someone could probably just Google sources of tritium because they would need this too, and they're not producing tritium. But maybe they are. I don't think they are. So no, because there's no lithium blanket with this, I don't believe. So it might be that they're just getting tritium from water, just like they're getting deuterium. So this is called inertial confinement rather than magnetic confinement. So this is in California. I believe this one's in California. This one is right here. That's the inside of it. I have, if you have my notes, if they showed up, it's kind of funny. They use this, I think, in a scene from one of the Star Treks or something like that. I believe. Does anybody see my notes?
Yeah, it's parts of Star Trek Into Darkness were filmed.
Into Darkness. Yeah. So I haven't seen that one in a while. I have to go back and watch it just to look for this. But this is in California. I'm not sure. This might be the same facility. I just can't remember where this one came from, but this one I know is California. So it's pretty cool looking. Sometimes it amazes me is our abilities to do things, and then we do some stuff that's just utterly idiotic when it comes to some environmental decisions. All right, so that summarizes this stuff right here, the nuclear basics of radioactivity, isotopes, half-lives, radon, and reactions, nuclear fission, how the reactors work, some of the key components to nuclear fission reactors, fission in general, you know, the isotopes that are needed, the reactions, that type of stuff, problems with nuclear energy, and then, of course, the basics of nuclear fusion.